Very good. Okay.
On space debris, and also welcome to the European Space Operations Center. Special welcome to Member of Parliament Klaus-Peter Wiltsch, to our Director General Jan Werner, especially pleased that he could make it today, and we will hear more from him today. Also welcome to Don Kessler, famous person in space debris research. We will hear from him later on as well. ESOC is a very operational site, as the name says. Currently, we have 17, I believe, spacecraft in operation, and this is why we are confronted with the problem of space debris on a daily basis, 24 hours a day, 7 days a week. And this is why already in the 70s, we started a research program on space debris. Actually, ESA is one of the founding members of the Interagency Coordination Group on Space Debris. Together with NASA, we started this in the 90s. And even though ESA satellites are not contributing much to the space debris population, we are very much concerned with it. And space debris is a global issue. We are all concerned about it, everybody who is flying spacecraft. And this is why I believe this problem can only be solved globally. If we all stick together, if we all put our resources together, this is, my opinion, the only way to handle this. At least ESA is ready to contribute our 40 years of experience and expertise to a global initiative. With that, I'd like to welcome you all once again. Hope you have a very fruitful, enjoyable, successful conference. Hope after the conference we know even more about space debris than before. And now I'd like to give the podium to our Director General, Jan Werner.
Yeah, good morning, ladies and gentlemen. On behalf of ESA as a whole, I would like to welcome you for this very important conference on space debris. Space debris, and you are all experts, but anyhow, I will guide you a little bit through the idea of space debris and some additional things in that direction. So first of all, space debris as a very general topic is of utmost importance. And of course, you see here the dinosaurs dying out because of a meteorite. This is a very special part of the story I would like to talk about. But first of all, I would like to show just an equation. The equation is very simple. It is what is risk, because risk in normal people are discussing a risk always in different ways. Most probably they are discussing about the probability only. But you see here, risk is the probability of something multiplied with the amount of damage or the effect, or however you call it. And this is a very important equation for our discussion about space debris as well. So if we now look into the equation, we have here the probability, we have here the amount of damage, and this would be a constant risk, meaning the risk is constant because of the multiplication of the two effects. Now this is a very special showing the graph. Usually when we have pictures like that, we change them a little bit and we make them on a logarithmic scale, and then you see you have just straight lines. So within these straight lines, each of these having the same risk, it is important to define something what is an acceptable risk. Let's assume this is the acceptable risk. I will not give any number, but this is important to understand what we are talking about. Because now we can say, okay, everything which is below this line is acceptable. Everything which is above this blue line is not acceptable. And now it comes that we go into details. Where are we? With amount of damage, if we are looking for people, of course, people, astronauts, etc., have a very high value. So therefore, we are something over here. If we are discussing about security-related system, might be over here. Infrastructure, think about Earth observation, telecommunication, and other things. And then we have operational systems, whatever it is. And then demonstration and test systems, which we have as well. And you see that the acceptable probability of failure depends very strongly on the amount of damage which might happen. And this should be the basis of what we are discussing. And when we are discussing about space debris, we are at least also in this area, because we are also endangering people in the lowest orbit. So therefore, this is the space debris developing over years and years, and it's said that now about more than 750,000 particles of a diameter of at least 1 centimeter are in our orbit. And as they are in the vacuum, what we need is a vacuum cleaner, very simple. But the simpler the words, the complicated the issue. And of course, you know the movie Gravity. There it was a very special effect. There were many mistakes in that movie. I will not go through that one. But the effect as such is a very serious one. And we know it, how serious it is, because we had with our Sentinel-1A, which was launched in 2014, we had an effect like that. You see here the solar panel, a picture of the solar panel after the launch. Everything is fine. And then in 2016, we suddenly found that the electricity production was decreasing. And when we looked again on the solar panel, we found here an impact of some particle, very tiny particle, but because of the high speed, it destroyed partially the solar panel. So it is not only fiction, not only science fiction like Gravity, it is facts. It is facts that space debris is really dangerous. And there are different types, of course. We are taking care, as Rolf was saying, we are trying to take care of all of these issues, but sometimes also things are happening, and this means, for instance, here, part of a rocket after launch fell down and destroyed a housing. So one would say probability is very small, but it happened. And I can tell you, the farmer was not happy at all, as you see, when he found these particles in his home. So it is a serious issue. We had another case, which was Rosat. This was a German satellite together with Americans and UK. It was launched. It had a mass of 2.5 tons. It is very nice. We could also show that satellites and space is not only for space, but also for lenses. So it was a really success story. But then it came to the point where it was not any longer operational. And because of some changes in the launch sequence, because it should originally be launched by a space shuttle and also catch up by a space shuttle, but then it was launched with a normal rocket. It came down, and I can tell you this night was one of my most difficult nights, waiting for the final. We were very lucky because it de-orbited here in the Gulf of Bengal and not overland, endangering people. And of course, the insurance companies are already using this as an argument for them to buy higher insurances. So you see here an insurance asking whether you should not take care of that. You know all about the collision between Iridium and Cosmos, producing even more space debris, and this was a certain issue as well. And we are discussing about mega constellations and what do we do in case of mega constellations with very cheap, inexpensive satellites, how to avoid that we get another space debris from that. One thing would be, and you are discussing about different things, also that we have a satellite collision avoidance system for satellites like we have in planes, and it is also developed now for trains. So why not have it in space? And concerning the deorbiting of bigger parts or maintenance, there are some ideas, but so far they are not really realized. And the reason is very simple, because to buy a new satellite, it's nice. To pay the same amount just for deorbiting is not what the different states are trying to do. And then we have, as I mentioned earlier already, also the danger coming from meteorites. This is Chelyabinsk in 2013. We know that there happened bigger things like that in the past, also dying out of the dinosaurs. But already here we had more than 2,000 injuries by that meteorite coming down. And it was a tiny one. This was the final impact in a lake. It was a very tiny meteorite. So, just a few months ago, on January 10th, we had a bigger one flowing by the Earth in a distance just between here and the Moon. So it is a big danger, and of course you know it, but we have to tell it to the world that we have to take some measures about all of these aspects, because such a situation may happen in the future, and we should better prepared and not say, okay, we will be on the Moon and have a nice view of the Earth. And it's also not that Bruce Willis is ready to do it again. He did it once, but that was sufficient for him, so we should have our own solutions for that. And therefore, planetary defense is an important issue. It is not directly what you are talking about here, but I think the overall situation has to be covered. Therefore, space debris, what we need for space debris is tracking, collision avoidance and removal in the future. For space weather, we need monitoring and forecast. For near-Earth objects, we need detection, prediction and countermeasures, and all of this, and this is my message, should be done in global cooperation, because this is very important. No, not one single state should say, I'm not interested in this field because of several reasons. I do it because of security reasons on a national basis. I think it's very important that you all promote, yes, you also, that you all promote the clear message that these are global challenges, and we should do it on a global basis, on a joint initiative worldwide in order to fight against these dangers we have in our space. ESA is ready to contribute by its own competence for space debris, for tracking and also for removal, for space weather, which is also affecting, for instance, the satellite navigation signals and near-Earth objects. So with that, I hope you will have a successful meeting, a successful conference, and I'm very interested in getting all the impulses from you to really do this also then on a political level. Thank you very much, and have a nice time here in Darmstadt.
Dear colleagues, good morning. My name is Holger Krag. I'm the chair of the conference, and as such, and on behalf of the program committee and the local organizing committee, I warmly welcome you to Darmstadt and the 7th European Conference on Space Debris. So we are now counting the 24th year for this conference, and I think we can really say that over time this conference has grown in a truly international event. This time we have an all-time high in registrations, which also underlines that we have not only a recognized event, but also the world's largest dedicated event on this topic today. We have received 350 abstracts and almost 500 registration effects. And that meant we could not consider all of them. For the first time in the history of our conference, we had to send people home. And we're in a situation where we had to select one abstract for oral presentation out of 3. So a very, very exceptional situation, and we apologize for everybody whom we could not consider. But I think this tells us already 2 things. Space debris is on the agenda everywhere, and we need a larger conference center. Now, if you look at this, you might get the impression that the interest in space debris is growing with the number of objects that we have in space. When my predecessor, Walter Fluri, founded this conference in 1993, the US Space Surveillance Network was tracking roughly 8,000 objects. Half of them were rocket bodies and satellites, and the other half were fragments coming from basically on-orbit explosion events. So the objects tracked are roughly larger than 10 centimeter. And you see there was a linear growth in the objects. And in 2002, the IADC, Interagency Debris Coordination Committee, published its guidelines for the first time. And we were hoping that we can stabilize this linear growth into a more sustainable trend. However, if you look at the situation today, the US Space Surveillance Network is tracking almost 18,000 objects, and only 7% are operational satellites, so the objects that we want to have in space. The overall mass accounts to 7,500 tons of hardware. And another notable difference, the majority are now fragments. And they come basically from two collisions, one voluntary one and one accidental one. And they appeared in the recent past. And the growth in the number of fragments has deviated from the linear trend of the past and has entered into the more feared exponential trend. And I will come back to this later. If you look at the situation today, we will find in space roughly 5,000 objects with sizes larger than 1 meter. Roughly 20,000 objects with sizes above 10 centimeter. These are the ones that we can hardly monitor from ground by surveillance systems. Talking about 1 centimeter, Jan Werner said it, 750,000 flying bullets of that size, and hardly countless for objects larger than 1 millimeter. 150 million is our model estimate for that. And we have seen from the example that our director has shown that even these small ones, we need to worry about them as well. Our operations team on the 23rd of August, an unforgettable day for all of us, noted a sudden orbit change and also an attitude change and a permanent power loss all at the same time. And this was very, very strong evidence of a hypervelocity impact. And then we reactivated an onboard camera that was used 2 years before to monitor the deployment of the solar arrays. And I think one lesson learned is we should fly these things on all spacecraft. It's very helpful. We were able to locate the damage. The damaged area has a diameter of 40 centimeter. And with all this data we gathered, we were able to determine that the impactor was man-made debris of 1 centimeter size, 0.2 grams, hitting it to the rear side. 7 fragments have been produced that are tracked now by the surveillance system. One of them generated a conjunction alert with the sister spacecraft, with Sentinel-1B, which is flying on the same orbit, but 180 degrees apart. So we were lucky with this still, because we can continue the mission. But if the object had hit into the main body, the outcome might have been much more severe. Now, this object was too small to be tracked, and there was no chance to avoid it. However, the 20,000 large ones, there is a chance to avoid it, and that's what we're doing here in ESA. Our operations team is busy 24/7 monitoring conjunctions for these 20,000 objects. We now have a fleet of 10 satellites in near Earth orbit, and I can tell you every week at least there is one high-risk alert to be followed, and we resulting in 1 or 2 maneuvers per year and per satellite. And that's today normal life in satellite operations. Flying collision avoidance maneuvers has become normal. Dear colleagues, let's now listen to some first-hand experience from a gentleman that actually has exposed himself to the environment. Unfortunately, he cannot be here himself. Although he's only 400 kilometers away, the problem is it's 400 kilometers in this direction. It's Thomas Pesquet, ESA astronaut, is currently on board of the International Space Station, and he will give us his welcome message now.
Dear participants of the Space Debris Conference, I'm very sorry that I cannot be here with you today, but as you can see, I've been held up somewhere and it seems like I still have a lot of work to do before they let me go back home. However, please be assured that I will closely watch what you do from above, since the topic you're working on is essential to the life of an astronaut. Our modules are shielded and withstand the impact of objects up to 1 centimeter in size. However, I had to expose myself to the environment of space during a spacewalk, and our spacesuit, however fantastic it may be, is much less resistant. So as exhilarating as the experience was, I could not forget what our ESA experts in Darmstadt explained to me, especially when I was able to see impact features on the surface of the ISS during my work. The ISS will also have to conduct a debris avoidance maneuver once in a while. Should the collision warning come in less than 24 hours until the event, a collision avoidance maneuver cannot be conducted anymore. In this case, our crew will have to close all the hatches and enter the safe haven, which is our Soyuz spacecraft, so that we can depart the ISS in case of a collision. This happened 4 times in the history of the ISS program. I really hope that you experts help to develop means and methods to avoid that I ever get into this situation. In my own interest, let me wish you a successful conference, interesting discussions, and think of us astronauts up here. So goodbye from space.
After this introduction, I would now like to explain you a few logistics of this conference, and don't worry, I will be brief on that. First of all, the most important thing that you have is your badge. You should wear it at all times, and it's also your access to the lunch buffet. So, very important. On the back side, you find the credentials to log into the wireless network here in the conference center, equally important. If you registered for the conference dinner, you should have a colored stick on it, and the color code indicates the menu option that you have chosen. So everybody who registered for the dinner, I kindly ask you to put your conference badge on the table in the restaurant with the sticker upwards so that the waiters can see what you ordered and bring you the right food. If you registered for the technical tour, you should have a black sticker on your badge. Now remember, this is a center where critical operations are performed, so don't explore it on your own, but stay in the conference center. Also, smoking is not allowed here unless you're in one of the dedicated smoking areas outside. Then please also watch your belongings. ESA is not liable for any losses. And I will leave it like that because in your booklet you found in your conference bag, you will have more detailed security instructions, and I don't need to repeat them here too much. What I need to do is to familiarize you with the conference center here. Our opening ceremony, the plenary session, and also the technical sessions will be right here. But after the plenary session, we will open the exhibition. For the first time, we have an exhibition in this Space Debris conference, and that will be done in the press conference center down here on the ground level next to the rotunda behind the space shop. We will open it right after this. And directly after that, we will open the lunch buffet. There are 2 lunch buffets, one in the press conference center and one outside of these doors. But we will open the one in the press conference center first, and half an hour later only that one. And that is the pattern we will follow throughout the conference. There will be these 2 lunch buffets. This one down here will always open first, and half an hour later, the one up here next outside of these doors. We also have a poster viewing center that is in the so-called Winter Garden on this level. If you walk out here to your left, you will find the posters, and there's a dedicated poster session with the authors present tomorrow evening at 18:30. Now, you all have the detailed conference program in your pocket, so there's no need to enter into the details, but there's 1 or 2 highlights I need to explain. So first of all, you find that the technical sessions are not synchronous, and that's not a mistake. We never do mistakes here in ESOC. So that is on purpose, because that gives us the opportunity to open the 2 lunch buffets at different times, and we can balance the load and the queue lengths between the 2 lunch buffets. Tonight at 18:30, you're all invited to reception in our canteen. There will be drinks and finger food, And the canteen is a building next to this one towards the main gate. Just follow the crowd. I think you can't miss it. For the participants of the conference dinner, there will be a bus service from the ESOC main gate. The conference dinner is on Thursday evening. Remember that the last bus will leave at 1840. And for the participants of the technical tour to Mannheim, to the Technomuseum, there will be only one bus, also leaving from the main gate, and that will leave at 1300 sharp. And remember, we are in Germany, so the buses leave on time, sometimes ahead of time. On Friday, we will have a press conference, and there will be a high-ranked panel consisting of the representatives of the sponsoring agencies for this conference. And I'm very glad to announce this. We will also have our director of the center, Wolf Densing, our director general, Jan Wörner, and the economy minister of Germany and aerospace coordinator, Brigitte Zypris. Now, this is an event primarily intended for the press, but as much as room allows and your interest, you're of course invited to follow this. Now I think I have overstressed your attention and it is time to relax a bit. And in order to do this, we have prepared a movie. And I think it's now time to enjoy the premiere of this movie. And if our technician is ready, then I ask you to put the 3D glasses on and we darken the room. And then I think you should also fasten seatbelts. And then I say action.
Dear participants of the Space Debris Conference,
Welcome to a journey of a different kind, one which brings us back to Earth. The objects we encounter along the way are man-made. Originally designed to explore the universe, these are now a challenge for modern spaceflight. We passed Pioneer 10 on its way to interstellar space. Now defunct, it has provided us with fundamental insights into our solar system. Space debris is not a concern out here, so let's rush on. Our gas planets have seen probes flying by. Only Jupiter and Saturn have had orbiting satellites. To prevent contaminating the planet's environment with terrestrial forms of life, they are safely disposed of. We are entering the region of the rocky planets. Besides Earth, Mars is the most observed. We can track the location of active probes orbiting the red planets, but not of their inactive predecessors. These uncontrolled spacecraft could become a risk to other missions. Before we enter our home planet's zone of influence, we pass by the so-called Earth-Sun Lagrange points. Here, a balance between forces allows spacecraft to move synchronously with Earth. Despite growing demand for the Lagrange points, especially for space telescopes, there is no risk of congestion. The balance of forces is only perfect at precisely one spot, and the slightest deviation will cause the objects to drift away. To prevent a return to Earth, ESA's former Herschel and Planck space telescopes have used their remaining fuel to bring them into an orbit around the Sun. The risk of a return is now close to zero. The next objects we encounter are on highly eccentric orbits, reaching from a few thousand to more than 100,000 kilometers altitude. These orbits are very sensitive to perturbing forces caused by the Sun and the Moon. To prevent long-term interference with frequently used regions due to drifting and uncontrolled reentry, ESA has modified the orbits of active missions such as Cluster 2 and Integral. The satellites will now re-enter within the next 25 years at safe latitudes. Let's continue and visit one of the most congested regions in space, the Geostationary Ring. This is the only orbit on which satellites move synchronously with Earth, an ideal choice for meteorological and telecom satellites. The average distance between two objects here is only 190 kilometers. Defunct spacecraft in geostationary orbit can drift and endanger satellites in their vicinity. This is why experts recommend to retire these objects at least 300 kilometers higher to a so-called graveyard orbit. With a successful lift, they should no longer interfere with the geostationary orbit. But can this be guaranteed for all times? Aging satellites are known to release debris, and explosion can occur due to residual energy sources. The resulting fragments can be thrown back and cross the geostationary orbit. The release of residual energy, once the nominal mission is completed, is therefore fundamental. Launcher stages used to deliver spacecraft into the geostationary ring often remain on their transfer orbit and could interfere with active missions. Consequently, debris mitigation guidelines foresee that these stages should be maneuvered out of the geostationary ring and other frequently used regions. Further along, we pass through the region used by constellations for satellite navigation. Like layers of an onion, 4 different constellations make use of 4 different altitudes. Inside these layers, we also find defunct satellites and upper stages. Stable graveyard orbits are difficult to find here. Fortunately, no explosive breakups have taken place so far. As we move even closer to Earth, we see that the number of objects around us is growing. This is the region of the low Earth orbits. 2/3 of all large man-made objects are concentrated here. About 600 active satellites provide us with science and Earth data and telecommunications. They are surrounded by thousands of defunct satellites, rocket stages, and fragments. Plus, this area is facing a surge in spaceflight activity. Smaller and more cost-effective satellites are increasingly launched to low Earth orbit. The only chance to ensure the future use of these orbits is to strictly apply debris mitigation measures. The first is to monitor the environment while spacecraft are still active. ESA satellites like Cryosat 2 have to perform 1 to 2 maneuvers per year to avoid collisions. The second measure to combat the harsh rigors of years in space is to release onboard energy by depleting fuel, venting pressure tanks, and discharging batteries. Finally, the longer spacecraft stay in orbit, the higher the risk of collisions becomes. Experts fear that one day, the cascading effect of collisions and follow-on collisions might set in making spaceflight in this orbit extremely difficult. A maximum of 25 years in orbit after mission completion is thus recommended. This can be achieved by moving the spacecraft downwards into the denser layer of Earth's atmosphere. In 2011, ESA successfully conducted such a disposal maneuver with ERS-2, lowering it from an operational altitude of 800 kilometers to 600 kilometers, where the remaining fuel was burned. Instead of otherwise 200 years, ERS-2 will now re-enter in less than 10. On their way down, objects pass through the altitude of another man-made object, our human outpost in space, the International Space Station. Although the environment here is relatively clean, it is not risk-free, as shown by the many impact chips on its surface and the regularly conducted collision avoidance maneuvers. In even lower altitude, uncontrolled objects are bound for a re-entry. To minimize risk, larger spacecraft must be brought down using a complex, controlled maneuver to a selected safe spot on Earth. Without such a maneuver, the time and location of re-entry are not under control. The uncontrolled re-entry will start after a final orbit revolution at about 100 kilometers. First, the aerodynamic forces will cause exposed external parts of the spacecraft to be sheared off. During deceleration, the object will be exposed to extreme heat. Some materials, such as aluminium, will begin to melt. The outer shell is gradually destroyed. Internal elements are released to the airflow and dissolve. In addition, strong aerodynamic deceleration enhances the destruction process. With complete disintegration, only components made of heat-resistant material, like titanium or glass, will have survived. They cool down and fall with a terminal velocity of about 300 kilometers per hour, mostly into the vast seas. Occasions to find space debris objects on the ground are very rare, and unlike meteoroids, they do not form craters. We have reached the end of our journey. Spaceflight has put mankind forward in the endeavor to understand our universe. It provides us with unique insights into our home planet and makes us aware of our responsibilities towards it. To ensure future exploration and exploitation of space, we need to tackle the challenge of space debris. The countermeasures described in this film are a first step. With joint and continuous efforts of all spacefaring nations, we will be able to achieve this goal.
Sounds like you like the movie. Very good. I hope you enjoyed it. If it went too fast for you, you can also download it from our webpage and watch it again. If you don't like it, I'm sorry, I'm afraid it's still on your USB stick that you got. Just delete it. But I personally think it is a great one, and I would like to cordially thank the team behind that movie who did do a tremendous effort in setting that up with a lot of dedication, with a lot of creativity, and I think it has become a great work. And I think it's also a good introduction to the conference, and it raises expectations for the days to come. Now, can you bring back the slides, Dirk? Yeah, thanks. Now, we have taken a look into the past, but now let's take one look into the future and follow in the footsteps of our keynote speaker. To do this, let me just highlight two major aspects that will certainly be discussed intensively during this conference. The first are the challenges coming with the deployment of large constellations in low Earth orbits. The novelty of many of the announced plans that you see here is that they combine a very large number of satellites with high orbital altitudes where the atmospheric cleansing effects are no longer existent. And if you keep in mind that in all humanity space flights since 60 years, the overall number of spacecraft we launched is 7,000. And that is going to be comprised in one or two of just these constellations in one mission. Now, to implement mitigation measures in a reliable manner for them will be quite a technological challenge. And this comes at a time where spacefarers of today already fail to implement mitigation measures to a sufficient level. And my office regularly monitors space surveillance data in order to form statistics on how well we actually behave globally in this regard. And this is one example here. This is for the post-mission disposal, so the requirement to remove spacecraft in order to avoid long-term presence in space after the mission. And 40% of all missions fail to implement this today. And as many of you know, in 1978, Donald Kessler has written a paper jointly with Burton Court-Palais in which he postulated that in a few decades from then, collisions might become the dominant source for space debris. And this cascade effect of collisions and feedback collisions was later named the Kessler syndrome. And in 2013, the Interagency Debris Coordination Committee concluded in an internal study that in some orbital altitudes, the space object environment might have reached an unstable state. And this might be some first sad evidence that Donald Kessler's postulations were right. While the growth of objects cannot be stopped without drastic measures like active removal, our current poor behavior is further accelerating this trend. And we need to do significantly better in adhering to the mitigation guidelines in order to contain the growth. And the longer we wait, the more costly any counteraction will become. And as spacefarers and space enthusiasts that we are, we should do everything to leave enough space behind for the spaceflight of future generations. And with this, I would like to introduce our keynote speaker, Donald Kessler. Donald Kessler retired from NASA in '96 as NASA's first senior scientist for orbital debris research. He began his career modeling the interplanetary meteoroid environment. He later applied the same modeling techniques to predict debris generation by collisions between artificial satellites in Earth orbit, leading to NASA's orbital debris program in 1979. Since retiring, he has continued to consult with NASA and other organizations. He recently chaired a National Research Council study, participated in 2 NASA Engineering and Safety Center studies, and represented NASA at the IEDC. Don has published more than 100 technical papers on meteoroids and orbital debris, and has been a contributing author or editor of a number of major reports. He has received the NASA Medal for Exceptional Scientific Achievement, as well as awards from various astronautics and safety organizations. Following this conference, he plans to devote much more time to retirement.
this goes in my pocket. Well, thank you. And this is really an impressive movie we've just seen. I'm impressed with all of this. And the size of this crowd speaks for itself in terms of how well the orbital debris program has grown over the last 40 years. I couldn't be more satisfied with it. And I think we owe a bit of gratitude to Walter Fleury for beginning this series of meetings. I was here in 1993, and I was impressed with it then. I'm even more impressed with it now. So ESA has come up with a really nice program. I want to talk today about actually the thing that started my thinking about debris in the first place, and that is that debris is really about all about the small stuff and their sources and how we manage that. And I want to, over the years, back 20 years ago, it was very obvious that the debris program had become balanced enough and well known enough that it was moving into an operational phase. And I think over the years, in developing that operational phase, some of the research has been skipped over that's necessary to really understand the whole environment and all the techniques that's required in order to manage the environment. And if you don't understand the sources, it's difficult to manage the environment. And I'll want to go over some of that stuff. But over the since the Iridium Cosmos collision, there's been a lot of activity taking place to describe exactly what is going on, and it made me much more familiar with what needed to be done. Some of those things that I've participated in was in the National Research Council study, where we ended up evaluating NASA's orbital debris program and ended up concluding that they were short on a couple of things. One was coming up with a management plan that predicted where the program was going and where it needed to go. And I believe that the whole international program probably needs something like that so that others can better appreciate what needs to be done and schedule it. We did that with NASA. The first 10 years we had what was called a 10-year program, and we met all of our requirements. That program consisted at that time of getting some good measurements and establishing an international community, and we did accomplish that. Then there were two studies that I participated in with the NASA Engineering and Safety Center. One of them was to assess NASA's new orbital debris, ORDM-3, because it was obviously a higher risk than previous models. And initially I was tempted to say, well, ESA's model is better than NASA's model, until I understood the data that was going into the new NASA model. And once that was understood and the effects of it, we ended up concluding that the NASA ORDM-3 model did represent the best measurement of the environment today. But it also had a lot of large uncertainty in it, and we recommended that there needed to be some in situ measurements of the debris environment in order to resolve that uncertainty. And finally, I'm currently involved in an engineering study to understand exactly what is the risk evaluation of present things that are in orbit. In other words, we got to the point with our first study that we wanted to know, are our predictions accurate in terms of how many satellites are failing? And so that study, we learned some very important things. First of all, it's a very hard study to do because most people are not that willing to release their information, and we ended up with people that wanted to have their data proprietary, and we could work with it on that basis. But the reports that are coming, that this one's going to come out, is a proprietary report. It's still in the process of being put together. But I do have permission to share one piece of information that I think is important. And that is that we found a statistically meaningful number of satellites that had events. That had events very similar to the Sentinel-1A. And we had a pretty large sample of satellites that we looked at, and more than 10% of them experienced events very similar to the Sentinel-1A, in that they had sudden momentum changes and there was all of those events occurred within about 45 degrees of the polar regions, which is what you expect for any solar sync orbits. The rate that these events occurred was identical to what was predicted from the measurements of haystack and goldstone radars, where we have a measure of what the flux is for those sizes, but the magnitude of the events was less. But when we corrected the mass of the debris that we were assigning to those sizes, for example, a 3 millimeter size, we normally would assume that it was a solid particle, but it's not, and we know it's not. And we have tests from the satellites, ground tests, where we've broken up satellites, and we have a relationship between what that mass is versus the radar size, which we use to calibrate the radar signals. So when we use that mass, which is a smaller mass, we got excellent agreement in terms of how many satellites would experience this momentum exchange. And it turns out that as long as you have sensors accurate enough on the satellite to measure these momentum changes, you can get a measure of what the mass flux is at those particular altitudes. And what it really boils down to, if you take all of the intact objects that are currently in Earth orbit, there's roughly about 100 of them per year that are experiencing these momentum changes. We just don't measure them because some of them are dead. And each time they're hit by these particles, they're of course generating more debris. So that is another source of debris right now. And which leads to why do we really need a lot more measurements. Back in the 1960s, when I first started working with NASA, just about every center was measuring the orbital debris environment with a satellite in orbit. And we defined a meteoroid environment at that time that's been good for nearly 50 years, just as a result of those measurements. Today, we have absolutely no in situ measurements above about 500 kilometers altitude. And the reason for that, the only reason that we have those is because of manned activities and the fact that you can look at the return spacecraft surfaces. So being able to monitor the debris environment at higher altitude is really a continuing problem, but also the fact that we do have these radar sampling techniques and that data, I believe, should be available to everybody to start looking for other sources of debris. And I want to run through some examples of how you would do that. For example, when we first got our haystack data, the first thing that popped out is, let's see what, there's the laser. Was this sharp point that most of the haystack, there was this very sharp peak at 900 kilometers, and our model said this stuff ought to be more evenly spread out. There's something going on there. And also because of the fact that all of this was at 65 degrees, it meant that that there was a source here. And all of this data is published in one of my publications in my website that you can download and gives you the full history of that. But we didn't know what that was. We later also analyzed some data from the Goldstone radar, and the Goldstone radar had these clusters of many objects would pass over at once, and they all fell along a straight line. And it turns out you can use that data then to say, well, what's the source of this? And it turned out to be Cosmos 1900, which was a Rörsat, and which led us to believe, well, Rörsats are also at 900 kilometers. There's much more of them, about 50 of them at that altitude. And that became then, the more we investigated, that became the way we came up with a Rörsat story. There are other stories that can be told if you can look at the data and you put it in the right format. But I haven't seen any of that done since that time. Now, most of the plots that we see today show the 10-centimeter population in just the 10-centimeter in larger population. Well, it's really about the small stuff, and it's because when I first wrote the JGR paper in 1978, I did not have a plot like this in it, But there was a plot in a 1977 paper that's almost identical to this. And I'm saying this not because to show how smart I am or anything like that. It's just the fact that it's so easy to come up with this calculation. Some people have done it with simply with a quadratic equation and a large particle in box and come up to the same kind of conclusions. I used a random sample and a programmable calculator to come up with a plot like this. But what we really need to know is what's going on at the smaller sizes. And the reason you want to know that is because it's the 1 centimeter to 1 millimeter size that's really affecting most spacecraft that they need to design to. And also there is another possibility that we need to look at, and that is the importance of secondary debris, the real small stuff, eroding spacecraft surfaces. Normally, when you take that 10 centimeter plot, you'd say, well, what's that mean to the small particle population? You can take the intact objects, add a mass to the minus 0.75, which is about the mass distribution you expect as a result of collisions. So if it were collisions only between large objects, you would have a plot that looks roughly like this. Well, what we've measured, though, is a plot that looks like this. Now, how do you explain this 1 millimeter population of where there's another mass density? And we get that from the space shuttle data, that is, and I'm sure Mark Matney is going to talk more about that in another presentation. But this is pretty solid at 400 kilometers, and of course we have measurements here from radar, and we don't have any measurements here. So we can't, it's obviously something different going on, and the question is what can cause it. And one of the things that I want to go back and mention, that there was an assumption made back when we first started the program, and that is that we assumed that we could ignore the erosion of small particles because there's a very small amount of mass in this end of it. But as time goes on, this amount of mass increases. But also, what if you have other sources of the small debris? We've got sodium-potassium particles. We know we got those. We know we've got paint coming off a spacecraft. We know we've got aluminum oxide as sources of independent sources of small particles that can act to erode these surfaces. And that could account for that. And if it doesn't, there's an experiment that flew back in 1984 on LDEF that was put together to measure the interplanetary meteoroid environment and was intended to detect small particles of natural meteoroids. What it ended up measuring is a whole bunch of streaks, similar to what was that I showed on for the haystack data. And each one of these streaks is most likely something that's generating small debris. And there are 15 of them on this particular slide. And in this case, just like the other plot, it's the time, this is the day of the year versus the longitude that they spot them. So every time the satellite would come around to the same longitude, it would run into a swarm of debris. Those need to be explained, and also they may be contributing to this type of a phenomenon. And finally, we need better models in order to handle that, and we need the measurements to test those models. To me, measurements and models go together. That should be a teamwork, where a modeler will predict something, somebody goes out and measurement, says you're right or wrong, and you adjust your models accordingly. And the fact that this is a statistical process that we're putting together does allow you the computer time required to do these 10 centimeter type calculations shouldn't take a lot of time, because we're only interested in the statistics as opposed to the exactly which object is hitting which object. And once you define an environment, you can use that environment to find out which satellites are the most vulnerable and you need to get rid of. So you don't need to recalculate that over and over. And of course, when you're doing just the statistics of an environment, you can get down to only two You only need to keep track of the perigee and apogee, and you don't even need to keep track of the inclination if you define the inclination relative to the Laplace plane. And in GeoSync, that could be make those calculations a lot easier. And then because we are talking about probability, we know that just because we have an average of 10 collisions per year predicted, that's not necessarily what's going to happen. There's one chance in that there's a significant chance that we'll not have any, and there's another significant chance that we'll have 4. So, and this illustrates a random run with the legend model, and you can see that in 50 runs you get 50 different environments. And so you could say that why do we plan for an environment that's only 50% probable? This is another one of those, this is a risk type thing. The consequences are severe in this. That is, we could have an environment that we can't use. So I would suggest that we need to plan for an environment something closer to 95% probability or 98% probability that it won't be exceeded, and rather than just this average environment. And there's also probability of solar effects that we can't predict what the future sun's going to be, but we do know what it's been in the past, and we can use that information then to assign a probability that we're going to have a certain amount of solar activity, and that too can go into the future models. And so what we really need then is better and faster models. We need more measurements, and we need to define exactly what is an acceptable environment, and what are we going to do, what are the acceptable techniques of maintaining that. And does that work? Yeah. If there's time, yeah, sure. Any questions? You have some amount of time.
Spontaneously agreed to take one question. Who's the lucky one? Nobody dares.
Okay, I'll be around if anybody wants to talk.
You have been perfectly clear.
Yeah.
Thank you very much, Donald. Deep in the pocket. Yeah, thank you. Thank you very much, Donald, for that very interesting talk. And it's really amazing to see how deeply involved you are to the roots and in the various facets of the space debris domain. So thank you very much for that talk. Dear colleagues, with this, I would like to open the conference. And I shall not do that without thanking our 6 co-sponsors. This is the International Academy of Astronautics, IAA. This is the Committee on Space Research, COSPAR. This is the Italian Space Agency, ASI. That is the French Space Agency, CNAS, the German Space Agency, DLR, and the UK Space Agency. And of course, I would like to wish all authors and experts here in the room, and many of you are experts in the fields of measurements, mitigation, modeling, hypervelocity impacts, space surveillance, active debris removal. I wish all of you fruitful and lively discussions, and I hope we do everything to make your stay as enjoyable as possible. And I would like to thank all the media representatives in the room for your interest. In the end, it's up to you, and it's because of you to help us to increase awareness for these problems and also for the solutions that we propose. Yeah, with this, I would like to turn over chairmanship to my 2 colleagues, Manuel Metz from DLR and Christian Cazot, who will run the plenary session, which will give you a good cross-section for the 130 oral presentations that we are expecting in this conference. Thank you very much.
Okay, so good morning everybody. My name is Manuel Metz and it's a pleasure to be chair of the first session. We have 4 highlight talks this morning here in this plenary before this room is split into 2 different rooms. We'll chair this together with my colleague Christian Cassot. And we have highlight talks from very different areas of space debris research. And the first one is on a modeling topic. It will be presented by Hugh Lewis from University of Southampton. Hugh.
Thank you very much. Good morning, everybody. It's a bit of a difficult feat to follow Don Kessler, so I'm going to do my best. We'll be talking about a modeling study that wouldn't have been possible without funding from European Space Agency through their General Studies program, and hard work of some colleagues that I'd just like to acknowledge from Technical University of Braunschweig, IFAC CNR in Italy, Belstead Research in the UK, Clyde Space in the UK, Airbus, and some colleagues at University of Southampton as well. So the talk is focused on a modelling study that we conducted on behalf of European Space Agency to look at large constellations and small satellites and what the impact might be on the environment. So this particular talk is going to be a very, very brief look at the study and the results that we obtained, and there's going to be some more detailed presentations throughout the week. So a bit of background, which I'm sure I don't need to share with you, but essentially what we're facing into the future is the prospect of some very large constellations being orbited into low Earth orbit. In particular, a couple of those, SpaceX, OneWeb, look as though their plans will start to be fulfilled from next year, and they'll be launching many thousands of satellites into orbits above 1,000 kilometers altitude. At the same time, we're also starting to see quite an upturn in the number of small satellites, especially CubeSats, being launched into low Earth orbit. And very recently, we all heard about the launch from India of over 100 small satellites that were deployed into low Earth orbit. So that's the background that we're facing. One of the interesting things that I did, a talk at the Royal Institution back at the end of January to the general public. And one of the things, we just finished a talk on space debris with colleagues from the Project to Drift. And we asked the public who were present whether they thought mega constellations were a great idea, having just talked to them about the dangers from space debris. So I asked for a show of hands to see who thought a mega constellation was a good idea, and nobody in the room put their hand up. So I'd just like to do the same thing again, kind of the academic in me. So who thinks a mega constellation is a good idea? And nobody in the room puts their hands up. Okay. So then what I did at the talk was to explain that actually it's not just about polluting space. Space debris and our work is not just about that. It's about enabling space activity and making sure that we can do that in a safe and a sustainable manner. I explained that these mega constellations weren't just there to generate space debris. That's not their primary mission. Their primary mission was communications. And in fact, delivering a service that the United Nations has said is a basic human right, and that 50% of the world's population don't actually experience. So I kind of gave them that context, and then I said again, who now thinks these constellations are a good idea? Everybody in the room put their hands up. So again, in that context, who thinks a mega constellation is a good idea if we're delivering 50% of the world's population, we're giving these really vital services? I saw one hand go up, so that's at least an improvement, a couple of others as well. So it's a tough sell to an audience focused on space debris, and I do appreciate that. So, but this is kind of motivation for the work, really, we're at the kind of brink of this kind of new commercial space age, and these large constellations and the small satellites potentially represent a risk to safe and sustainable space flight. But it shouldn't be about waiting for these things to happen and then trying to fix the problem, which is what we've been doing for the last 50, 60 years. It should be about defining things that are clean, making sure that actually they go into the environment in a sustainable way. So that really has been the motivation for this particular work. So what we did as part of this study was to first of all, review what had been done in the past, both in terms of the activities involving small satellites and constellations, but also the work in terms of the modeling of those activities that have been undertaken. That then led us to start to investigate particular parameters that were important, or we felt were important, with respect to constellations and small satellites, using 3 evolutionary models. In our case, very different to, as you've just heard, we only focused on the 10 centimetre population and larger. So we weren't, at that time, we weren't looking at the smaller population. Our belief, which we did back up with evidence, was that it was the larger elements that were important. So then we conducted the simulations and then kind of took a step back and tried to analyse what we saw. That was made slightly more challenging. We were able to use supercomputer for this activity. So a typical kind of space debris modelling study might have maybe tens of different cases. In our particular study, we were able to employ a supercomputer to look at beyond 350 different cases, which really enabled us to explore the situations. So you'll hear from me now, or you'll also hear throughout the week a number of presentations which I would like to direct you to as well. So I'm going to describe the study setup, and I'm going to talk about some of the results. Obviously, I can't share with you 350 different results, so I'm going to summarize very briefly for those. Okay, so our kind of a basic starting point was an, if you like, a reference population. So this is a population and an evolution without the small satellites involved and without the large constellation involved. And it's essentially it's derived from studies that we conduct at the IADC. So in this particular case, what's really important to take away, I'm not going to go through every single bullet point here, but what's important to take away is this is a representation of a population that is very, very successful at conducting space debris mitigation. If you look, it's 90% compliance with the post-mission disposal requirement. We're not considering any explosions in the future environment for this particular reference scenario. So it's already of what we would call a very, very optimistic point of view. And then what we do on top of that is we add in a constellation, or we add in small satellite traffic. So in terms of the constellation traffic, we looked at a synthetic constellation consisting of just over 1,000 satellites, organized in 20 orbital planes, and this was an altitude of 1,100 kilometers, which is more or less where the large constellation proposals are intending to go. And then we essentially built up this constellation and then replenished it over a period of 50 years in the simulation, and our simulation period extended out for 200 years. Not because we believe that, we understand what the space traffic is going to be like in 150 years. It's really to enable us to start to understand the trends that start to emerge. And then what we did with this constellation case is we took all of those parameters and we varied them. So we changed the altitude, we changed the size of the constellation, we changed how many satellites were successful in terms of the post-mission disposal. We changed what we considered with respect to the launch vehicles. So all those parameters were varied, and that enabled us to start to understand how sensitive the debris environment were to those particular constellation parameters. And then we kind of did the same thing with the small satellites. We looked at 3 particular launch rates, but our baseline case was essentially reaching the launch of 270 small satellites per year. Now, you may think that's a lot, but we're currently looking at between 100 and 150 small satellites being launched each year at the moment. Okay, so 270 is not that much of a stretch. And in our case, in this baseline scenario, what we did is we considered launches that were very similar to the launch kind of pattern today in terms of the altitudes and the orbits that they were going into. So many of these satellites will be deployed at the ISS altitude, for example. But for small satellites, as opposed to the Constellation, no post-mission disposal we consider for these as a baseline case. But again, we started to vary that. We looked at what would happen if the small satellites were able to add in a propulsion system or some kind of device to comply with post-mission disposal. So our Constellation case, and again I'll emphasize this, the Constellation case has already very, very good compliance with existing space debris mitigation measures. That's the baseline case. And we wanted to see what would happen if we then varied those. So I'll take you through some of the results from this study, and just again point out a couple of more presentations that will be taking place on Thursday for these. So I'll focus on the Constellation study first. And this is the result from our baseline case. So this is the 1,000 satellites. 90% of those satellites would then be complying with the post-mission disposal rule, which is, in our case, it's about a 20 to 25-year rule that we looked at. So we had 3 evolutionary models. And what you're seeing there on the left-hand side is the number of objects that we predict over the 200-year period. On the right-hand side, it's the number of catastrophic collisions. So those are the collisions where the energy is greater than 40 joules per gram of the target. And you can see that the solid lines represent the averages, and then we've also plotted the standard deviation around each of those averages, so you can see that. And as Don has mentioned, that uncertainty is actually very, very important. What we see down at the bottom there is the number of objects that we'd see at the end of the simulation period. So the 3 different codes that we used generated different amounts, but then we compared that back to the reference population of the same year. And what we see is that all the models there predict about a 30% increase as a result of the presence of that constellation by the end of our simulation period. But a much higher impact in terms of those catastrophic collisions that we're seeing. Some of those catastrophic collisions will be involving only the constellation satellites, but some of them will also be involving satellites that aren't part of the constellation. Nevertheless, you can see already with an introduction of a large constellation which is compliant with, at 90% level with mitigation guidelines that exist today, we see quite a substantial impact on the environment. So then what we do is we start to vary some of the parameters. So one of the factors that emerged as being the most important was this post-mission disposal and how successful the operator would be with respect to that. So we varied that parameter from 60% all the way up to 100. And what you see on the chart here, the top one is the number of objects that we predict in the environment at the end of the simulation, and this is the average again, so I've extracted the average, so do be careful, there's some uncertainty around that. The bottom figure is the number of catastrophic collisions. So you can see at 60% compliance, the environment doesn't really end up in a very good situation. Nearly 100,000 objects bigger than 10 centimeters that we're seeing at the end on average, and about 300 catastrophic collisions. The situation improves quite drastically as we get towards very high success rates with post-mission disposal. But what's really important here to understand is that even if we have 100% success with post-mission disposal, that does not mean that there is no impact on the environment. And in fact, what you see is that the satellites on these decaying orbits that take 25 years, they are actually interacting with the background population in those 25 years. And that's where we see some of the impacts. And that kind of situation emerges, and we can see that coming through, but there is something we can do about that. We just make sure that those constellation satellites don't take long to deorbit, so much less than 25 years. So what you're seeing here, this chart, the surface plots. On the top again, it's the number of objects that we see at the end of the simulation. On the bottom, it's the number of catastrophic collisions. This time we're plotting not just the success rate with post-mission disposal, but also the lifetime of those disposal orbits. And what we see in particular, it's a very small red dot, but if we have 95% success rate with post-mission disposal and the lifetimes of these disposal orbits are very short, then actually we're down here with about 26,000, 27,000 objects, and also 40, 45 catastrophic collisions. The reference population, we had 37, 38 catastrophic collisions. So we're kind of bringing it back in terms of the impact on the environment. But you can see, even at 85% compliance with the post-mission disposal, we almost double the number of catastrophic collisions, we double the number of objects we see in the environment. So actually, it's really, really important that constellation operators are able to comply with this particular guideline. It's absolutely fundamental. Then what we did in all the previous studies that have been looked at, we ignore the impact of launch vehicles that actually deploy their constellation. So what we did is we did a worst case scenario. We assumed that all those launch vehicle upper stages remain in orbit after they've deployed the satellites. But then we released the satellites at different altitudes. And what you find is that if you release the Constellation satellites at low altitude, the launch vehicle upper stages will not remain on orbit for very long. And in fact, they're compliant with the existing debris mitigation guidelines. So something that emerged quite quickly from this is that launch vehicles should release their satellites at low altitude. Then you don't need to worry about the impact of those launch vehicles on the environment. But then it does mean that those Constellation satellites then have to climb up to the required altitude through propulsive means. But actually, it was one easy way of reducing the impact from the launch vehicles. Constellation size is an interesting one. So our original constellation was 1,000 satellites. We took that up to just over 4,000 satellites in the study. And very quickly, what you see is that there's a significant impact on the environment the larger the constellation. And it's non-linear. So in the sense that as you increase the size, the impact on the environment increases non-linearly. And that's something of concern. So, you know, some of the proposals that we've read about in the last few months, 4,500 satellites, maybe more, that potentially is a bit of a concern. In terms of the satellites themselves, another way in which you can mitigate the impact on the environment is actually to make them small, both in terms of their cross-sectional area and in terms of their mass. What this does is reduce the collision cross-section area, which essentially, coming back to the first talk of the day, the risk is equal to the probability times the consequence. You reduce the probability of the event taking place by making the spacecraft smaller. You reduce the consequences by making the mass lower, okay, because that releases fewer fragments as well. So something to think about in terms of designing those satellites is smaller is probably better. Obviously, that does then limit capabilities and so on. So there will be a trade-off that is going to emerge. There were lots of other results, and I'm more than happy to discuss with you on an individual basis what those results were, and I've got a summary at the end. With respect to the small satellites, so CubeSats and slightly larger satellites, there's a poster here that you can look at. I'm not going to go into too much detail on these because there's another poster which looks at that. So I've only really got one set of results to show you with respect to the small satellites. So this is our baseline case. So this is 270 satellites launched per year on top of our kind of basic population. And again, what you see at the bottom there are the numbers that we would see at the end of the simulation, the average numbers again. Okay, so the chart on the left in number of objects, chart on the right is the number of catastrophic collisions. And we see with that 270 satellites launched per year, the small satellites, there's a big impact on the environment, both in terms of the number of objects and in terms of the collisions that we would expect to see. The difference here, though, is that there are fewer opportunities for us to actually adjust the design of the satellites. So it makes our life a little bit harder. One of the things that emerged, though, was with respect to where those satellites actually end up. So if the satellites are released at relatively low altitudes, then you can actually mitigate some of the impacts. If those satellites are going into higher altitudes, then they're in long-lived orbits and they will cause us some problems. So what we see is that the impact of those launches is actually quite significant in the higher orbits, much worse than our background population that we had. In terms of the launch rate, even if we stick to the current launch rate, about 100 satellites per year, we still see impacts on the environment. Number of objects increasing by about 30% on average, number of catastrophic collisions increasing by about 50% on average. And that's with the current launch rate. So there's, again, a particular issue. So that's all I have on the small satellites. And I do encourage you to go and look at the poster, talk to Jonas, who did the work on the small satellites, to understand really in detail what was going on. So it just leaves me with a couple of things to say. I've taken a slightly different approach from the first presentation you saw this morning from the Director General in terms of defining risk. I come from a disaster risk reduction background, so I have a slightly more complicated equation to share with you. But basically what we want to try and do is reduce the risk to the environment, reduce the risk to other operators. So our study allowed us to look at lots of different parameters. And one of the things that you want to try and do is reduce the exposure to the background population to things like small satellites and to the constellation. That's the way to do it. So the things that we found, you need to have a very high post-mission disposal reliability, short lifetimes on those disposal orbits. Ideally go for smaller constellations rather than larger ones. Keep the constellation lifetime short. Our simulation, we had 50 years. The longer the constellation is active, the worse the impact on the environment. The satellites themselves, if you can keep them on orbit for a longer period of time, then you don't need to replenish them. You don't need to launch as many satellites. That's a way to reduce the risk. Release them at low altitudes, allow them to climb up under active control. That's another way to mitigate the impact of the launch vehicles. Adding in removal of the failed satellites on orbit. Again, we've shown that actually that has a significant impact on the risk. Add redundancy, add spares into the constellation, okay, because that, again, enables you to reduce the number of satellites that you're launching with spares, if you're able to switch over to a spare satellite. And the other thing to do is we've looked at typical constellation designs, Walker Delta, Walker Star. What we also did was we looked at what happens if you separate the orbital planes in terms of altitude. And what you see again is you can reduce the impact on the environment if you start to do that. Keep the satellites small. Make sure you've got good knowledge to enable you to perform collision avoidance maneuvers, and so on. And then with respect to the small satellites, you can see immediately fewer opportunities to actually mitigate the impact. Launch them to low altitude, keep the launch rate as low as you possibly can. Start to think about dedicated launches to these low altitudes. And again, see what we can do about improving the technology to allow the disposal of those satellites, to remove the mass from orbit. It's interesting, you know, the things that we found. That the preconceptions that we had, mega constellations, a bad idea. But actually what we discovered were the things that you can do to mitigate the impacts of these constellations. We only looked at one constellation. We had some simulations looking at multiple, and more work is needed to look at that. But actually there are things that we can do. Small satellites are a bit more of a problem. And I think that really does mean that we need to engage with that entire community to try and figure out how to achieve this sustainable future. So that's all I have for you. Thank you very much for your attention.
Thank you, Jung, for this very interesting talk, showing the results of European studies on the orbital population. And then I think that it will be extensively discussed during the conference, because this topic is very interesting. We have constellations in front of us. We have a lot of CubeSats in front of us. So we have to find the right way to avoid debris population increase. So now, as debris concern is, I will say, a world concern, we will virtually cross the Atlantic Ocean, and GCLU will give us a talk on the highlights in the US on this subject. Thank you. So GCLU is in charge of the Space Debris Office within NASA.
Good morning. The European Conference on Space Debris is one of the most important debris events for the international debris community. Unfortunately, due to sequestration and other restrictions, the last time NASA participated in this event was 12 years ago. So we, today, 11 members of the NASA Orbital Debris Program Office, that's almost half of the entire office. We are very glad that we are able to attend the conference this week. So on behalf of the team, I would like to share some highlights of our recent activities with you in the next 20 minutes. Before the highlights, I will first give you some background, the history of our organization, and then talk about the ESMCAT, the Pembroke telescopes, the space debris sensor, DebrisSat, Orbital model, and the recent update to the NASA procedural requirements to limit the generation of orbital debris. The NASA Orbital Debris Program Office is the only organization in the US government conducting a full range of orbital debris-related research activities. This unique NASA capability was established by pioneers, including Don Kessler, Joe Loftus, Bert Copley, and others at the Johnson Space Center in Houston 38 years ago. The roles and responsibilities of our office are defined in the high-level NASA requirement document. We provide technical and policy support to the NASA headquarters, NASA mission offices, the OSTP, and other US government and commercial organizations. We also represent the US government for orbital debris-related activities at the international level, such as the IADC and the UN COPIUS. We conduct the end-to-end research on orbital debris. We use ground-based radars and telescopes, in situ measurement, laboratory experiments to collect data on orbital debris. We then use the data to build different models for different applications. The satellite breaker model, the engineering model, evolutionary model, and satellite reentry survivability models, and a whole bunch of other supporting models. We then use the model to support NASA mission offices, including satellite reentry survivability assessments. We evaluate the benefits of mitigation and even remediation to support the development of policy for long-term environment management. And of course, we work and coordinate with the international community to address the orbital debris problem. Data is the foundation of everything we do at the NASA Orbital Debris Program Office. So here you're looking at the data we use for orbital debris in our office. Here we are looking at altitude from low Earth orbit all the way to geo region for orbital debris from 10 micrometers to 10 meters in size. Ground-based radars and telescopes can only detect and measure orbital debris about 3 millimeters and larger in low Earth orbit, and about 30 centimeters and larger in geo region. For sub-millimeter debris objects, we rely on in situ measurements, i.e., we look at the inspection result from the window and radiator panels of the space shuttles and a few surfaces returned from space. And as you can see from this coverage chart, there is the need to extend the debris coverage in geo, and also there is a gap for millimeter-sized orbital debris in low Earth orbit. So the first two highlights I will show you next intend to address the geo debris coverage and this gap in low Earth orbit. The NASA's optical assets on Ascension Island is the result of a collaboration with the Air Force and the Air Force Research Laboratory. The observatory is located on Ascension Island. It provides a unique longitude coverage for geo debris from near the equator. There are two telescopes, The big one is the 1.3 meters ES-MCAT telescope with the field of view of 41 arc minutes. We are planning to build a smaller telescope, 0.4 meter Benbrook telescope with a similar field of view. And the goal of the project is really very simple, to have 2 telescopes fully dedicated to orbital debris observations. Right now, we are testing the operations of the ES-MCAT telescope. There are different observation strategies, but the most important mode is to conduct a survey of faint and small objects in GEO. We will also target objects with low inclinations in low Earth orbit and also use the telescopes to provide rapid response for new breakup events and to support other space situational awareness applications. The ES-MCAT, the telescope, achieved the first light 2 years ago, and we conducted its user readiness review in last August. We plan to install the small Benbrook telescope with the goal to reach full autonomous operations for routine GEO debris survey in 2018 or 2019. To address the millimeter size debris gap, the Orbital Debris Program Office, we have led the development of technology for in situ measurements since 2002. The DRAGONS system is a sensor package that combines different impact detection technologies to maximize the information that can be extracted from individual detected events. The data that we can collect from DRAGONS include the impact time, impact flux, the size of individual impacting particles, as well as the impact speed, impact direction, and impact energy, which will allow us to estimate the material density of the impacting particle. The International Space Station program has funded a technology demonstration mission for DRAGONS, but to avoid the confusion with the SpaceX Dragon capsule, the mission was renamed Space Debris Sensor. And the objectives for the SDS are, number 1, to mature the DRAGON technology, and number 2, to measure the sub-millimeter debris populations at the station altitude. The Orbital Debris Program Office, we completed the fabrication of the SDS flight unit. We deliver the flight unit to the NASA Kennedy Space Center, and we completed all necessary pre-flight testing and integration of the flight unit last December. So right now we are on schedule on SpaceX 13 to launch to the International Space Station on November the 1st for a 2-year mission. As we prepare for the launch and operations of the space debris sensor, the NASA Orbital Debris Program Office continues to seek opportunity to deploy DRAGONS to altitude above 600 kilometers. And the reason for that is very simple. Don mentioned this 2015 NASA Engineering and Safety Center study in his keynote speech. This report released 2 years ago by the NASC concluded that, number 1, particles smaller than 3 millimeters, they represent the highest penetration risk for most spacecraft. And in situ measurements is really the only feasible, effective means to measure such small particles above 600 kilometers altitude. And this is very important for NASA, because as of today, NASA operates close to 20 missions between 600 and 1,000 kilometers. Yet we had no data, no direct measurement data to characterize the #1 penetration risk to those missions. Therefore, the #1 priority for the NASA Orbital Debris Program Office in the coming years is to identify mission opportunities to deploy Dragons above 600 kilometers altitude. Another important project for the office is called DebrisSat. This is a collaboration with the Air Force Space and Missile Systems Center, the Aerospace Corporation, and the University of Florida. The objectives are, #1, to design and fabricate a 56-kilogram spacecraft, we call that DebrisSat, representative of a modern spacecraft in low Earth orbit, and then to conduct a hypervelocity impact to catastrophically break up the DebrisSat. And then after the breakup, we process, collect the fragments, and measure the physical properties of the fragments, and then use the data to improve the satellite breakup model and other space situational awareness applications. The DebrisSat test and the pre-test shot on a small launch vehicle markup, we call that Debris LV, they were successfully conducted in 2014. And right now we have an army of students going through the piles of the fragments to carefully process the fragments, extract fragments from the soft cast form panels, and measure the physical properties of the fragments. The data include the mass, the dimensions, the shape, material density, and a gigantic digital image database. Once we have the data from the DebrisSat, we will use the data not only to improve the satellite breakup model, but also we will develop a shape distribution for the future order model to better assess the impact damage from orbital debris. We also plan to conduct additional laboratory measurements, radar and optical measurements on a subset of DebrisSat fragments, so we can use the data to improve the radar debris size estimation model and to develop a new optical size debris estimation model. As I mentioned earlier, data is the foundation of everything we do at the NASA Orbital Debris Program Office. And ORDEM is a perfect example of how we utilize the data to build a model that's used by the global debris community. ORDEM is an engineering model. It provides a mathematical description of the environment and can be used by satellite designers and operators to assess the orbital debris impact risk to their vehicles. This model really combines all the data that we have, plus the Air Force catalog data and all the modeling capability we have. So it's really our best estimate of the current and future orbital debris environment. The latest model, ORDEM 3.0, was released in 2013. ORDEM 3.0 covers the debris populations from 10 micrometers to 10 meters in size, from LEO to GEO. A simple material density distribution is also provided for debris components, the sodium-potassium, degradation fragment, and fermentation debris. Uncertainties in the debris flux predictions are also included. Right now, we are working on a new version, ORDEM 3.1. The objective of ORDEM 3.1 is to simply update the debris populations with more recent radar and optical measurement data. We plan to release ORDEM 3.1 to the community later this year. For future ORDEM, the next generation ORDEM, we will, in addition to the radar data from HUSA, HAX, and Goldstone data, we also incorporate the ES MCAT telescope data the space debris sensor and debris set data to look into the possibility of, for example, adding a shape distribution and other model improvements so that we can better use the model to assess the risk for future missions. The first NASA mission requirements for orbital debris mitigation, they were established in 1995. Currently, we have 2 documents for orbital debris mitigation at NASA. A high-level policy document is the NASA Procedural Requirements for Limiting Orbital Debris, NPR 8715.6b, detail specific requirements for missions, such as the preservation and the 25-year rule. Those requirements, they are provided in the technical document. We recently completed an update to the procedural requirement. This updated version better clarifies the roles and responsibilities of different NASA organizations. The ODPO, we are leading an effort to update the technical document. The main focus is to provide more and better technical justifications for the existing requirements. To conclude, I will share our vision for the next 5 to 10 years with you. We will continue to expand the LEO-to-GEO debris measurement coverage for better environment definitions. We want to conduct in-situ measurements on millimeter-sized orbital debris at 600 to 1,000 kilometer altitudes to address the top risk for NASA missions. We want to advance modeling capabilities to improve orbital debris impact risk assessments for future missions. We will utilize debris set data, as I mentioned earlier, for a shape distribution and for other potential improvements for ORDEM 4.0. We will continue to work with the US and the international communities to improve the global efforts on orbital debris mitigation and to assess the potential benefits of remediation so we can come up with a long-term strategy to manage the orbital debris problem. Thank you.
Okay, thank you very much, JC, for this overview of NASA activities, and good to have you here again at the conference after 12 years, you said, I think, in the beginning. I think this is very good, and also for sharing your visions for the future. Now, the next highlight talk brings us a bit closer to the vacuum cleaner that the General Director mentioned this morning. It will be presented by Satomi Kawamoto, and she will talk about activities that are being performed by JAXA on the topic of active debris removal.
Okay, thank you very much. It's a great honor for me to be here to present our activity on active debris removal at JAXA. JAXA has been studying cost-effective active debris removal for many years with background of experiences through autonomous rendezvous and docking by ETS-7 or HTV, or image processing to locate target object, or autonomous navigation by Hayabusa, or space robotics. And now ADR study is conducted as one of the four study from recently organized research team for space debris comprehensive measures. We believe that the cost is very important for active debris removal because debris evolutionary models show that ADR of currently existing more than 100 debris objects should be removed, or more than 5 debris objects per year should be removed for stabilizing the environment. Not a single removal demonstration is enough to stabilization. So if the cost is too expensive, the ADR cost is expensive, alternative countermeasures such as launching replacement spacecraft in case of damage will be less expensive, and then the ADR will not be realized. However, the debris-related cost, this is cumulative debris-related cost, increase every year. And the ADR, or as well as post-mission disposal, require temporary cost, but it can suppress the future increase. However, the break-even point is in the future, in the distant future, the active debris removal will not be realized. However, it is too late to start ADR after the cost is unacceptable in the future. So if the ADR cost is not so expensive, the break-even point comes earlier, then ADR can be conducted as one of options. So we believe the ADR cost is very important to start ADR sooner. So we define our target of ADR as follows. First, we define our target object is large intact debris, because this is a source of countless small debris which pose direct risks to the spacecraft. However, the spacecraft, small debris is very difficult to remove and inefficient and costly. So we think that the source of them, the large intact debris in a crowded region, should be removed. And we set our highest priority to the low Earth orbit because there are some crowded orbit exist. And we think that the removal spacecraft will be used to remove debris, because sweeper or laser is also proposed, but it is difficult to remove large debris at this moment. And these require large spacecraft in orbit, and it can give much impact in case of failure. So small spacecraft would be better. And as for the type of debris, there are both rocket upper stage and satellite, but we think that rocket upper stage should be the first target, because both technologically and non-technologically, rocket body is less challenging, because its shape is almost cylinder and no appendages such as solar paddles that pose a collision risk in a proximity operation. And its shape is axisymmetric, and no complicated motion such as tumbling will be occur. And also by some light curve observation or radar observation, this is observed by German radar, the H2 rocket body, Japanese rocket body. It shows that almost stable attitude motion due to gravity gradient. So there are some tumbling objects, but there are also some rocket body with almost stable attitude motion. So it is easier to capture it. And design details are less confidential than satellite. So we set rocket body as a first target. This shows the our operation scenario of removal. The first removal satellite should be launched into orbit and make a rendezvous to debris object in crowded region. Because the debris targets are uncontrolled, non-cooperative object with no reflector, no marker, no handle to capture. So non-cooperative rendezvous is difficult compared with the conventional cooperative rendezvous. And after it comes too close to the debris, some proximity operations such as motion estimation and attachment of a propulsion system, here in the tether is attached, is required. And then the orbit is required. So we propose the start technology demonstration from the less challenging object in lower altitude and rocket body with almost stable motion because it is less challenging. And after that, the target range will be expanded for rotating debris or satellite debris and so on. Because if we can build the technology, technologically feasible and economically viable, international discussion may be activated because at this moment there is no technology for remove debris is available, so no blame is assessed for leaving debris on orbit. However, if the technology is available, maybe the discussion can start. So we propose to start the ADR technology with less challenging target. So I will introduce some key technology studied at JAXA. First is non-cooperative rendezvous and vision, some navigation sensors such as visible camera or infrared camera are studied. And first, the target object can be observed as a point. So angles only navigation is studied, and then it switched to model matching navigation. And then it's a payload attachment fitting is a capture point. Such navigation is studied. So navigation filter design is studied, and rendezvous simulation has been conducted, and linear covariance analysis has been performed. Also, passive abort safety for avoiding collision in case of failure has been studied. And after the debris satellite, removal satellite come close to the target, final approach using vision sensor is studied. The image processing to identify relative distance at altitude is studied, and some numerical simulations and on-ground experiment using this kind of optical simulator, which use the debris scale model with sunlight or a screen background, and some measurement experiment has conducted. And as for the attachment of propulsion system, we study attachment of tether end without need for precise position control is studied. The most suitable capture method depends on how to apply thrust to the debris. If we pull through the tether, we don't need to care where the capture point or just hooking is enough when we pull through the tether. However, when we push the debris object, we need to control the center of mass. So we think that the pulling by tether is less challenging. So one idea is use the simple extensible boom to spread inside the payload attachment fitting of rocket upper stage. Some numerical simulations or on-ground experiment has been conducted. Another idea is using harpoon or puncture. Harpoon will be ejected from a distance, but the puncture will be ejected after touching the wall of the debris. Or another idea is robot arm and stretching gripper to capture both payload attachment fitting or rocket nozzle of rocket upper stages, and some experiment is conducted. And as for the e.deorbit, we think one of the promising method, electrodynamic tether system, is studied. Electrode tether system can generate enough thrust via the interaction with geomagnetic field, and it can remove large debris object within 1 year or so. And this method will not require any propellant or high electrical power, and it is also suitable because its thrust is small and no thrust vector control required, so attachment operation will be less challenging. So, however, this EDT technology is not so mature, so we plan the demonstration of small EDT on H2A transfer vehicle has been studied. This HTB is a Japanese cargo ship for supplying ISS. The HTB number 6 was launched last December, and this endomass was deployed from HTB after its detached ISS. However, this endomass that store tether could not be released from HTB, and unfortunately tether was not deployed. Now the cause of problem is investigated, but most probably cause is one of 4 actuators. This endomass has 4 actuators to be fixed to HTB for avoiding unexpected release during ISS docking phase. However, one of these actuators could not be separated, so unfortunately the tether could not be deployed. However, the field emission cathode, which is electron emission devices mounted here, this field emission cathode was operated without critical troubles, and its ability to emit electron to plasma is better than expected. This is a ground experiment, and this is a on-orbit experiment result. So, because the tether is not deployed, so the electrons were collected from the positive part of HTB instead of the tether. FEC is key devices to achieve propellant-less propulsion for cost-effective ADR. And the tether liberation control using the thrust of HTB or electrical current was also studied, and the tether was not deployed, but technological level of EDT was advanced by analysis and ground test during deployment phases. So our next demonstration plan is now being re-examined. We also conducted some system study. We studied a small satellite around 200 kilogram to be launched as a part of dual launch or piggyback launch, or launched as a cluster in the future. We also studied a tethered tag using a conventional chemical or electrical propulsion to tow debris with tethers. So that's all. Thank you very much for your kind attention.
Thank you, Satomi, for this very interesting talk on the activities performed by JAXA in the field of active debris removal. The coverage of the topics is very impressive, and I think that we will have a lot of discussion during the conference on this subject. And as you said, a key element for active debris removal is knowledge of the debris itself. So is it possible to have a better knowledge with the observation? It's perhaps something that Thomas Schildknecht will explain to us. So Thomas is from the University of Bern, and he will give a talk which is determining and modeling space debris attitude states by fusing data. So Thomas.
Thank you very much, Christian. So it's a pleasure for me to give you some insight in some measurement projects which are going on. And in fact, I'm going to tell you about attitude states, modeling attitude states by fusing data from different techniques. It's about space debris, but in this particular context, let me say that space debris is real debris, but also referring in this context to any object where you have lost contact with. So why are we caring about attitude states? And let me give you a few examples. The first one is active debris removal. Attitude state of an object which is a target of a removal mission is one of the really critical parameters of an active debris removal mission. We need to know the rotation rate, tumbling rate, axis of rotation, and when I say attitude state, I really mean not just the spin rate, I mean the orientation of the spin axis, both in the satellite fixed coordinate system, object fixed system, and in the inertial frame. This is an example of the ESA e.deorbit mission, where you have a tug which is grabbing the object. In this case, you have a nice model of the bird here. It's NVSat, and imagine if this object, the target, is spinning. You really have to know the spin rate, because many of these missions have an upper limit for the spin rate of the order of 5 degrees a second. Let me give you an additional example. Contingency support. So if suddenly your satellite up there is going to be silent, you really want to know what's happening. First of all, you like to know, is it still, in one piece? Secondly, you want to know, what's his orientation? What's his attitude? Because, to have the slightest chance to recontact the satellite, you need to know when its antenna is pointed towards your Earth station. So it could also be in cases where some satellite is not functioning normally again. You still have contact, but you don't know what's happening. So just to give you one example, this is the example of the Xmm Consent Contingency. This was an X-ray satellite of ESA, which became silent on October 18 in 2008. Nobody knew what happened. And we went off and took optical observations, and you see them on the left-hand side here. Hoping that this is working. For whatever reason, it's not. Anyway, we found, first of all, the satellite was still in one piece. And secondly, looking at the what we call the light curve, the change in brightness, we also found that the satellite was still perfectly stable in attitude. And this was a lot of help for the operators in this establishment here, because they could eventually regain contact with the satellite, I don't remember, a month after the fact, actually. So the third example I want to give you is one which is less obvious, perhaps. We have been hearing about collision avoidance maneuvers, conjunction assessment a lot this morning. And in order to do that, you need a catalog of orbits of all the objects you would like to avoid a collision with. So we need improved catalogs. Improved catalogs means, first of all, improved measurements, of course, but it also means improved modeling, forward modeling, propagation of the orbits. In order to do that, you need to take into account non-gravitational forces, and many of these forces, like air drag, solar radiation pressure, depend on the attitude state of the object. So you need to know the attitude state, ballistic coefficient, and some other details in order to improve the forward modeling or propagation of your orbits, in order to improve safety of operations by being able to conduct conjunction assessment and eventually collision avoidance. Okay, there's an ongoing ESA study on every attitude, motion, measurements, and modeling. Some of the results are going to be presented in this conference here. All the illustrations I'm going to show you are from the Swiss Optical Ground Station and Geodynamics Observatory in Zimmerwald, and you see on the right-hand side our 1-meter telescope. And this is just for convenience. By no means I want to give the impression that this is the only observatory producing this type of observations. Pure convenience. And I want to refer you to a series of papers in this conference. There's an entire session on Wednesday morning dedicated to attitude. A lot of the results from several studies are going to be presented, so that's why I'm not going to show you the details. Anyway, what type of techniques are available, let's say ground-based techniques, to estimate the attitude or determine the attitude state of an object in space? So one of the techniques is radar, synthetic aperture radar imaging. Get nice images. You have seen some of them this morning already. Another technique with radar is to look at the radar cross-section changes. It's a kind of radar light curves. We have classical optical techniques, optical light curves, change of the brightness of an object. We could also try to do direct imaging depending on the altitude of the satellite. If it's a lower satellite, then there's some chances that you can do direct imaging. And we have satellite laser ranging. So we can range to space debris which carry a retroreflector array. This is called cooperative targets. We can also range to non-cooperative ones which don't have a retroreflector array. It's more difficult, and it's still an open question how much we can do with non-cooperative targets and SLR techniques. So let me first introduce that radar technique. I should not start with a disadvantage, actually. The disadvantage compared to optical systems, of course, they're more costly. The range law is 1 to r to the 4th versus 1 to the r square for optical. Of course, the big advantage is you can use them during all weather conditions, even if the sky is cloudy, as today, while optical you can't. The attitude determination techniques, as I mentioned, one of them is the variation of the radar cross-section. But the other possibility is that, or the other technique is that you do imaging by exploiting the relative motion between the radar and the object. This technique is called inverse synthetic aperture radar. Resolution is range independent. That's the nice thing about it. No disturbance through atmospheric turbulence. But, this is important to notice, you have to determine the attitude state from the same data you're using to generate your image. So on the left-hand side, you see the idea. On the right-hand side, you see a radar image from the Fraunhofer Institute here in Germany. And it's important to notice a radar image is not what we are used to see. You know, it's something like the cross range here is Doppler, and the range here is really the range measured by the radar. It's, yeah, you have to get used to that. And as I said, the challenging limitation of the technique is that you have really to estimate the attitude states, the object motion from the data itself. So the image formation and the determination of the attitude are closely interlinked. So if you get a series of nice radar images and you think, oh, well, just looking at the images, I can deduce the attitude motion. Not really good idea, because it's already in there when you generate the images. So a cross-check with other techniques is highly desirable for this technique. So on the right-hand side, you see the radome of that famous radar here in Germany, which was used to come up with all the images I'm going to show you in this presentation. So the next technique is passive optical. We call it a light curve when you take measurements, consecutive measurements to measure brightness variation of an object. We can also do direct imaging, perhaps, to some large objects. And in order to determine the attitude, you think of direct inversion, you know, just getting the light curve and then come up with the attitude state of the object. This is only possible for simple shapes, only if you know the shape. So in most cases what we do is what I call forward modeling. You come up with a model of your object, start rotating that model and see how it matches with the observations. So I hope that this movie is playing. Oh, it does. Okay, this is a series of small subframes taken in order to get a light curve of a small 1Q CubeSat, Swiss cube, by the way, at the distance of about 1,000 kilometers. And you see the brightness variation of the object, which then can be turned into a light curve. So sometimes the object is pretty bright, sometimes it's even fainter than the detection limit of the system. This is another technique where we have been taking a long exposure, or rather long exposure, of a GLONASS satellite, defunct GLONASS satellite, and if you look carefully, you see this line here, and some glimpses here, and you can turn this into a light curve as well. That's another technique how we are acquiring light curves. Imaging, lucky imaging, or you can use very expensive adaptive optics system, whatever you do. In principle, you have to, get around the atmospheric turbulence. You have been seeing these images from amateurs. This is not a very good example here. This is the entire space station at about 3,000 was about 1,000 kilometers distance. So the idea is you can use a rather small aperture telescope, short exposures, freeze kind of the atmospheric turbulence. The technique is limited to large objects, bright objects, or very sophisticated adaptive optics techniques. satellite laser ranging. So this is a view, a nighttime view of the satellite laser ranging station in Zimmerwald in Switzerland. What you see is a green laser beam. In fact, this laser beam is not continuous. It's very short pulses of about a few centimeters in length. And what you do is you measure the round trip between the moment you are sending out the laser. It's reflected by a retroreflector at the satellite and comes back, and the light is collected with a telescope. So this round trip time you can then convert to a distance. So there's several techniques to use that to come up with attitude motion of objects. Just imagine you have a satellite like Envisat here, you have somewhere a retroreflector, and if the satellite is spinning, that retroreflector will spin around the center of mass of the satellite. And you will see range variations here of the order of a few meters here due to the fact that the satellite, the retroreflector is not in the axis. And the retroreflector has an offset with respect to the spin axis. If you're unlucky, it's actually in the spin axis, then you don't see anything. There's another technique. If you have a retro like this one, you can even see the sub-reflectors here. If you have a high repetition laser like a kilohertz laser data, this is some of this data here, where you see the individual reflectors if this cornicube is rotating around its axis. These type of measurements have been pioneered by the colleagues at the Graz Observatory in Austria. Let me give you a few examples of light curves. I mean, that's all nice, you know, and yeah, we come up with spin rates and axes and so on and so forth. But let me give you a flavor of how difficult it is, actually. This is a light curve of one of our objects we have been observing, and there's always seconds here, and you see the brightness variation. If you see this, something like this, you know, oh yeah, there is signal here, but what's the period of that signal? We don't know with this short measurement here. That's a nice one. Nicely periodic. Okay, probably this is the spin period. Perhaps from here to here, that's the spin period. I don't know. You know, front side, back side of an object. Wow, this is a high resolution light curve of an upper stage, actually. It's an N1 rocket body in LEO orbit, and the spin rate is just amazing, you know. This is of the order of 5 seconds. So this is front side, back side, spinning with a period of 5 seconds. I don't know if our Japanese colleagues are looking for these type of targets for their first experiments for the active debris removal. I don't think so. So sometimes it's more difficult. This is a GLONASS, a defunct one. A lot of aliasing. If you do a proper treatment of that data processing, you can come up with what we call a phase diagram, and you see nicely the front side and the back side of this guy here. Another important object, because it's one of the potential ADR targets, is the Japanese ALOS satellite. And if you look at the light curve, we are puzzled. We think this is a tumbler. It's not spinning around. It's not a simple rotation motion. It's really tumbling. We have been seeing a lot of changes, especially for this satellite here. These are 2 light curves here from spring 2015, very similar to different epochs. If you looked at the satellite in fall the same year, oops, really totally different and consistently different. Something happened between spring and fall this year with this satellite. So this also tells you monitoring over time is really important because things can change. This is a fast tumbler as well, an Ariane upper stage. You also see changes in the spin rate. This is the spin rate changes over a short time period here. You know, this is the spin period actually. So it spun up and then decelerated again. We see these very frequently in eccentric orbits, for example, GTO orbits. For some of the objects, we have simultaneous observations. This is an Envisat light curve, and at the same time, we have satellite laser ranging residuals. So, the question came up, how can we perhaps take advantage of having different type of measurements at the same time? This is just to give you one of the results. I mean, there will be much more and much more recent results on that. So the spin down of Envisat, you see the period here, the spin period over time. So it clearly spins down. It's what you would expect, that this spin is going to be damped out. Actually, the rate here is not really consistent with the models, but this is interesting. That's why we do science. That's why we do these measurements. So, challenge for the models. Data fusion. In most cases, the attitude states cannot be directly derived from the measurements. Neither from light curves, in most cases, neither, in some cases, yes, but in some cases not from satellite laser ranging. And as I told you, the attitude, the spin rate and attitude motion, which has to be determined from the radar measurements to generate synthetic aperture radar images. In easy cases, it's doable. If you have tumblers, it's getting very difficult. So, as I said, light curves, yeah, it's possible if you have good knowledge of the shape, and it's a simple shape. A simple cylinder like this one, yes. The problem is you don't know the optical properties of the surfaces, you don't know the BRDFs, as we call it, and so on and so forth. You need a wide range of geometries covered with your observations, otherwise no chance to really get the full attitude state. SLR is somewhat more straightforward, because for all the SLR, cooperative SLR targets, you have the models. You exactly know where this retro is with respect to the center of mass, and you have the shape of the object as well. So from just the visibility constraints, you see the retro. Once you don't see it, you can constrain somehow the possible attitudes. But often you have some assumption on the spin axis in the body fixed frame. That's often done. And yeah, as I said, ISAR inherent attitude determination, but it's not always possible. So all approaches fail if the tumbling motion is really complicated. So we should fuse that data. Ideally, what you would like to do is to estimate the attitude state, the full attitude state, so axis in the body fixed and inertial frame, directly from the fused data by a least square parameter estimation. Yeah, let's do it. But the problem is we don't have good models for these observations. All these techniques are missing some of the models which are required. For example, we don't have these, scattering properties of the surfaces in the case of optical observations. We have a similar issue in radar. We don't know the object's properties really in the radar. Unknown radar scattering properties. So what we do in a first step, instead of doing the ideal thing, which is our goal, of course, we do forward modeling, or we need forward modeling separate first for each technique, try to model what we see in the observations, and then combine two or all of the techniques. One way of doing it here at ESA is we use an in-orbit tumbling analysis simulation tool, which is a sophisticated tool, including a lot of physical models, to do that forward modeling. Just give me an example what you could do. I mean, if you would have, or if you have, as we do, two different light curves at two epochs, T1, let's say you have a light curve. You do the forward modeling, for example, with iota. You get an attitude state at this time. You have a second light curve at a different epoch here. And then you try to propagate that attitude state, or I mean, you don't try, you propagate that attitude state here to the second epoch using, you know, sophisticated physical models, including all the orbit perturbations or orbit models and torques you're expecting, and then try to compare this or to match this with the second light curve. Obviously, you will have to iterate that. That's one thing we do. Another way is to compare different techniques. Again, start with a light curve as an example, come up with spin rate, attitude state, hand that information over to the radar people, which then use that as an input to try to generate their radar image. Again, you can do iterate. You could do it the other way around, of course, you know, and include all the techniques I have been describing to you. This is the state we are today in terms of data fusion. It's first steps, because we first have to better understand the physics, the models, in order to represent our observations properly. We have a lot of details in the observations, much more than we can model right now. So this is just to give you an example, this is an example of satellite laser ranging forward modeling. In principle, what you observe is this here. You know, that modulation of the range, which is due to the fact that the retro is rotating around the center of mass of the object. But the raw measurements are awful. You know, there's a lot of other biases in these measurements. So what you try to do, you try to come up with a 6-parameter attitude state, trying to determine these 6 parameters in order to fit your measurements here. Has been done, and I'm going to show you a short movie on how this looks like. You know, this is Envisat here. This is a real measurement. This is the retro spinning around here. You have an observation here from Zimmerwald in this particular case, and this is what you see in the modulation of the range here. This is, you know, this is really attitude motion derived from the real data for Envisat. Again, we have simultaneous observations here. This is SLR, so range residuals, and this is the optical. If you look at it, much more details here in the optical from surfaces which are reflecting. I mean, it's not surprising if you look at this mock-up here. I mean, there's a lot of things you will see in the optical, direct reflections, and so on and so forth. Much too complicated, actually. So, in summary, attitude states are important for active debris removal, contingencies, orbit determination, propagation, just to name a few. There's other applications out there. I have been showing you 3 different observation techniques. But the important thing to notice is no attitude states can be directly derived from the observations without making some more or less justified assumptions, and that's why we need fusion of all this data. We try hard. We are just at the beginning of a long road, probably, but the first attempts are very promising, and I hope to be able to show you more, and you will see more in the sessions to come. And with that, thank you for your attention.
Okay, thank you, Thomas, for this very interesting talk. I think we will have much more details on all the topics during this week, and I'm very much looking forward to these. Now, I have to say that our colleagues from ESA, they have disappeared. So I don't know where Holger and Tim are. Okay. Okay, so with this, maybe.
Okay, so now next step is the opening of the exhibition. So I invite you all to go with us down 2 levels to the press center, where we will have the opening of the exhibition. And on the way out, please give back the glasses, the 3D glasses. Thank you. And then we'll reconvene at 2 o'clock for the start of the afternoon sessions.